Hello and welcome to Chapter 6.1, Ionic Reactions. This chapter will also include SN1, SN2, E1, and E2, but let's talk about just some of the basics of kinetics and reaction dynamics before we get into those specific problems. First thing we need to talk about is the energy diagram. And the energy diagram is a schematic representation of the energy changes that take place as the reactions are converted to the products. What this means is that things plotted on the y-axis are related to the energy of the reaction, where things plotted on the x-axis are related to the progress of the reaction or the change in the reaction. The energy difference between the products and the reactants is considered the delta G, or change in Gibbs free energy. So the transition state is the highest point in the energy diagram. Old bonds are partially broken and new bonds are partially formed. This is not an intermediate, this is a transition state. The higher the transition state, the less likely the reaction is to occur, meaning that it took that much energy to make the reaction happen. The more energy it takes to happen, the slower the reaction occurs, the less energy it takes to happen, the faster the reaction occurs. And the difference between the transition state and the starting material is that energy of activation, or what we like to call the delta G double dagger, E sub A, or E sub act. All of them are related to the energy of activation of the transition state. So what does that look like when we look at it as a plot? So again, looking at the figure at the bottom left, we have the free energy is increasing from the bottom up, and the reaction coordinate, or basically the time in which the reaction happens. Okay, so the x-axis is the reaction coordinate. It indicates the progress of the reaction in terms of the conversion of reactants to products. The free energy of activation, or activation energy, is the difference between the energy of the reactants and the transition state. The free energy change is the total energy difference between the reactants and the products, and the top of the energy corresponds to that transition state for the reaction. So, when delta G is less than 0, we're considering that exergonic, meaning that it gives out free energy. If it's endergonic, then delta G is greater than 0. This is similar but not the same to exothermic, where the delta H, or heat of reaction, is less than 0, or endothermic, where the delta H of formation is greater than 0. But in most reactions, because we're looking at our temperatures happening fairly close to room temperature, or not specifically very high or very low, the terms exergonic and exothermic and endergonic and endothermic can often be interchanged. But the concept here is that we are really looking at the change in free energy, not necessarily the change in enthalpy. So if we go to a set of reactions where the reactants actually have a lower energy than the products, we're now looking at an endergonic reaction. Notice that the reactants are lower than the products, but the activation energy, or the transition state, is higher than the products. This is typical for all of these reactions. Okay, so the difference between an intermediate and the transition state is that an intermediate can actually be isolated. So in the reaction above, where we have these butene reacting with HBr to do an addition reaction, we have the electrons from the double bond acting as the nucleophile to start bonding to the hydrogen. When it does this, the electrons from that double bond are forming that new bond with the hydrogen, and the bromine hydrogen bond is starting to break. So that's our initial transition state. When we move to the next step of the reaction after the transition state has happened, we now have a positive charge on the carbon and a negative charge on the bromine. These are intermediates in the reaction. Okay. Now that bromine has a negative charge and there's a positive charge on the alkane, we have the bromine acting as the nucleophile to go and take those electrons and add it as a new bond to that carbon, giving us our final product, which is the addition product of our hydrogen bromide across the alkene double bond. Okay, so this transition state is literally almost imaginary in the fact that these are partially formed and partially broken. They can never be isolated and are always shown in brackets with that double dagger to indicate it's a transition state. Okay, the intermediate is the chemical species of the reaction that can be isolated or can be measured spectroscopically. For example, we can see that carbocation happened. We can actually trap it with either the bromide or something else to show that it did exist in an intermediate state. Okay, so if we have an energy diagram for a two-step reaction, what we're going to have is we're going to have two energies of activation. The first energy of activation is going to be when the first intermediate is formed, and then there's going to be a slight hump or a slight dip in the energy curve. That is the energy of the intermediate. Now that intermediate has to undergo preferably a much smaller activation energy, but it still has to undergo some activation energy to form its second transition state where it's starting to form that next bond. Once it forms that next bond, it gains energy and therefore goes downhill to give us our products that are much below the energy of the transition state or either of the activation energies. Okay? The two energy diagrams are combined to form the energy diagram for the overall two-step reaction. Each step has its own energy barrier and the transition state at its maximum energy for each of those transition states. Okay, so now the difference between kinetics and energy is that kinetics is all about the rate of the reaction or how fast it goes. Now this is determined partially by the sterics of the system, but also the more energy it takes to get to your transition state, the slower reaction rate you're going to have. So in the case of here where we have our activation energy is lower for one reaction than the other, the lower reaction energy is going to go faster. Now we can also increase the reaction rates by increasing concentration or increasing the temperature. Okay. Note that the delta G, which is the Gibbs free energy change, the enthalpy energy change, and the equilibrium constant don't affect the reaction rate. Only that activation energy affects the reaction rate. These do, however, affect the equilibrium and the relative energy of the reactants and products, but not the rate. The rate is all about time. All right, so rate is a measured amount of the product formed per unit time. So if we start with a certain amount, we look for it to decrease, or we look for the product to increase, and the rate at which it increases is constant for each reaction. A proportionality constant tells us how easy it is to overcome that energy or reach that transition state and an independent reaction and is independent of reaction concentration. The larger the rate constant, the faster the reaction rate. Okay, so this allows us to do what we can develop a rate law. The rate law is equal to the rate constant times the concentration of the reactants. And it is experimentally determined by either watching the starting materials decrease or the products increase over time. All right, so let's look at this reaction here where we have B is reacting with our nucleophile C, which has a negative charge, to create our negatively charged leaving group, which is our A minus, and our BC new bond. Okay, so for single step reactions, the rate constant contains the concentration of all reactants. For example, if the reaction happens all at once, the concentration of both AB and the concentration of C are important for the rate step, and therefore they are included in the rate law. In multi-step reactions, the rate equation contains concentration terms for only the reactants involved in that specific step. And typically it's the rate determining step or the slowest step in the system. The rate determining step is always the slow step in a multi-step reaction, and it tells you that once you form that intermediate, it quickly reacts to form the final products. The order of the rate equation is equal to the sum of the exponents of the concentration term of the rate equation. So if you look at the bottom right, we have the concentration of AB, and it technically has an exponent of 1, and the concentration of C minus, which also has an exponent of 1, we add those together, hence the sum, and that gives us 1 plus 1 is equal to 2, so this is a second order rate equation. If the rate equation was double for one or the other of those components, we could actually have a third order or a half order or a 1 order rate equation. But it's always the sum of the exponents of the concentration of the reagents. All right, so in a multi-step reaction, the slow step is always the rate determining step. And you can think of it as this example on the right where we have sand coming through a series of hourglass type shapes. The smallest constriction where the sand can come through is going to determine how fast the sand goes through. If the sand goes through that slowest or smallest orifice first, and then it can quickly go through all of the other wider openings, then that becomes the rate determining step. Likewise, if you had it quickly go through other intermediates until it gets to the last reaction, for example, if we flipped the entire thing upside down, then the last step would be your rate determining step. In most reactions, the rate determining step is typically the first step in the reaction, and the rate determining step is always the slowest step in the reaction. Okay, so in a two-step reaction has a slow rate determining step and a fast step. So that means the reaction can't happen any faster than that first step that has to happen. And therefore, only the concentration of the reactants for the rate determining step need to appear in the rate equation. For example, in the reaction where we have AB splitting to give us A minus plus B plus, and if that's the rate determining step, we only need to show the concentration for AB because the concentration of C doesn't matter, since it can't react until the first step has happened. And therefore, that means that if it's only the concentration of the AB, that means we only have a single exponent above the concentration of AB, giving us a first order reaction rate. All right, so how do we determine reaction rates? First of all, we have to do it experimentally. So let's take the example of this reaction between hydroxide reacting with methyl chloride to give us methanol and chloride ion. So initially, we would say our rate is equal to the rate constant times the concentration of methyl chloride times the concentration of hydroxide. Okay, and so then we would actually put these two together at a constant temperature and monitor changes in either the formation of methanol or the removal of the methyl chloride from the reaction. So let's look at the table down below, and if we look at experiment number 1, we start with an initial concentration of the methyl chloride at 1 millimole and the concentration of hydroxide at 1 mole. We find the rate to be around 5 times 10 to the minus 7. Okay? If we double the concentration of methyl chloride and keep the concentration of hydroxide the same, we see a doubling in the rate of the reaction. Okay, so that's indicating that maybe we do have this, 1-to-1 reaction ratio. Let's do another experiment. Let's go back to number 3 and say, okay, we're going to use the same initial concentration of methyl chloride again, but we're going to double the concentration of hydroxide. And we see the same doubling of the initial reaction rate. That's indicating that hydroxide is important to the reaction rate and that the concentration of the methyl chloride is reaction rate. But let's double check this. Let's do another experiment where we double both of the systems. When we double both the methyl chloride concentration and the hydroxide concentration, we see a quadrupling or 4 times the initial rate. Okay, so what this tells us is that our reaction rate is based on the concentration of both the methyl chloride and the hydroxide. If we double either one of the concentrations of either reagent, we see a doubling of the reaction rate. If we double both concentrations of both reactants, then we get a quadrupling of our reaction rate. Okay, so how does that affect it when we look at equilibrium? Well, when we have equilibrium, we actually get a special relationship because we have to compare the rate of A going to B and the rate of B going to A. So if we have a reaction that can form A and goes from A to B, but then there's some back reaction available to us for B to go back to A, we have to take that into account. And so what we'll end up doing is taking our forward rate and our reverse rate are the same at the equilibrium. Only at the equilibrium is the forward rate and the reverse rate the same, meaning the concentration effect of A versus B is giving us where our equilibrium lies. And therefore our equilibrium constant is equal to the rate of the forward reaction over the rate of the backwards reaction, or the rate of the product over the concentration of the product over the concentration of the starting material. Okay, and so this is typically determined experimentally, and we can also do it by knowing the rate constants of the forward and reverse reaction. We can actually predict what the final concentration of A and B will be.